I'm thinking about buying a restaurant. So I go and ask the current owner, what is the distribution of the number of customers you get each day? And he says, oh, I've already figured that out. And he gives me this distribution over here, which essentially says 10% of his customers come in on Monday, 10% on Tuesday, 15 on Wednesday, so forth and so on. They're closed on Sunday. So this is 100% of their customers for a week. If you add that up, you get 100%. I obviously am a little bit suspicious, so I decide to see how good this distribution that he's describing actually fits observed data. So I actually observe the number of customers when they come in during the week, and this is what I get for my observed data. So to figure out whether I want to accept or reject his hypothesis right here, I'm going to do a little bit of a hypothesis test. So I'll make the null hypothesis. I'll make the null hypothesis that the owner's distribution, so that's this thing right here, is correct. And then the alternative hypothesis is going to be that it's not correct. That it is not a correct distribution. That I should not feel reasonably okay relying on this. It's not the correct. I should reject the owner's distribution. And I want to do this with a significance level of 5%. Or another way of thinking about it, I'm going to calculate a statistic based on this data right here. And it's going to be a chi-square statistic. Or another way to view it is that that statistic that I'm going to calculate has approximately a chi-square distribution. And given that it does have a chi-square distribution with a certain number of degrees of freedom, and we're going to calculate that, what I want to see is the probability of getting this result, or getting a result like this, or a result more extreme, less than 5%. If the probability of getting a result like this, or something less likely than this, is less than 5%, then I'm going to reject the null hypothesis, which is essentially just rejecting the owner's distribution. If I don't get that, if I say, hey, the probability of getting a chi-square statistic that is this extreme or more is greater than my alpha, than my significance level, then I'm not going to reject it. I'm saying, well, I have no reason to really, assume that he's lying. So let's do that. So to calculate the chi-square statistic, what I'm going to do is so here we're assuming the owner's distribution is correct. We're assuming that the owner's distribution is correct. So assuming the owner's distribution was correct, what would have been the expected observed? So we have the expected percentage here, but what would have been the expected observed? So let me write this right here. Expected. I'll add another row. Expected. So we would have expected 10% of the total customers in that week to come in on Monday, 10% of the total customers of that week to come in on Tuesday, 15% to come in on Wednesday. Now to figure out what that actual number is, we need to figure out the total number of customers. So let's add up these numbers right here. So we have, let me get the calculator out. So we have 30 plus 14 plus 34 plus 45 plus 57 plus 20. So there's a total of 200 customers who came into the restaurant that week. So let me write this down. So this is equal to, so I wrote the total over here. Total, ignore this right here. I had 200 customers come in for the week. So what was the expected number on Monday? Well, on Monday, we would have expected 10% of the 200 to come in. So this would have been 20 customers, 10% times 200. On Tuesday, another 10%. So we would have expected 20 customers. Wednesday, 15% of 200. That's 30 customers. On Thursday, we would have expected 20% of 200 customers. So that would have been 40 customers. Then on Friday, 30%. That would have been 60 customers. And then on Friday, 15% again. 15% of 200 would have been 30 customers. So if this distribution is correct, this is the actual number that I would have expected. Now, to calculate our chi-square statistic, we essentially just take, let me just show it to you. And I'll write it, instead of writing chi, I'm going to write a capital X squared. Sometimes someone they'll write the actual Greek letter chi here, but I'll write the X squared here to show that and let me write it this way. This is our chi-square statistic. Chi-square statistic. but I'm going to write it with the capital X instead of a chi because this is going to have an approximately a chi-squared distribution. I can't assume that it's exactly, so this is we're dealing with approximations right here. But it's fairly straightforward to calculate. We take, for each of the days, we take the difference between the observed and the expected. So it's going to be 30 minus 20. 30 minus 20. I'll do the first one color-coded. Squared divided by the expected. So we're essentially taking the square of, almost you could kind of view it, the error between what we observed and expected, or the difference between what we observed and expected. And we're kind of normalizing it by the expected right over here. But we want to take the sum of all of these. So I'll just do all of those in yellow. So plus 14 minus 20, plus 14 minus 20 squared over 20, plus 34 minus 30 squared, 34 minus 30 squared over 30, plus, I'll continue over here, 45 minus 40, 45 minus 40 squared over 40, plus 57 minus 60 squared, 57 minus 60 squared over 60. And then finally, 20 minus 30 squared, so plus 20 minus 30 squared over 30. I just took the observed minus the expected squared over the expected. I took the sum of it. And this is what gives us our chi-square statistic. Now, let's just calculate what this number is going to be. So this is going to be equal to, I'll do it over here so we don't run out of space. Let me do this in a new color. I'll do it in the orange. This is going to be equal to, this is what? 30 minus 20 is 10 squared, which is 100 divided by 20, which is 5. I might not be able to do all of them in my head like this. Plus, actually, let me just write it this way, just so you see what I'm doing. This is going to be 100. This right here is 100 over 20. Plus, 14 minus 20 is negative 6. Squared is positive 36. So plus 36 over 20. Plus, 34 minus 30 is 4. Squared is 16. So plus 16 over 30. Plus 45 minus 40 is 5. Squared is 25. So plus 25 over 40. Plus, the difference here is 3. Squared is 9. So it's 9 over 60. Plus, we have a difference of 10. Squared is 100 over 30. Plus 100 over 30. And this is equal to, and I'll just get the calculator out for this. This is equal to, we have 100 divided by 20 plus 36 divided by 20 plus 16 divided by 30 plus 25 divided by 40 plus 9 divided by 60 plus 100 divided by 30 gives us 11.44. 11.44. So let me write that down. So this right here is going to be 11.44. This is my chi-square statistic, or we could call it a big capital X squared. Sometimes you'll have it written as a chi-square, but this is approximately, this statistic is going to have approximately a chi-square distribution. Anyway, with that said, let's figure out, if we assume that it has roughly a chi-square distribution, what is the probability of getting a result this extreme, or this at least this extreme, I guess is another way of thinking about it. Or another way to say, is this a more extreme result than the critical chi-square value that there's a 5% chance of getting a result that extreme? So let's do it that way. Let's figure out the critical chi-square value. And if this is more extreme than that, then we will reject our null hypothesis. So let's figure out our critical chi-square value. So we have an alpha 5%. And actually, the other thing we have to figure out is the degrees of freedom. Degrees of freedom. The degrees of freedom here, we're taking 1, 2, 3, 4, 5, 6 sums. So you might be tempted to say the degrees of freedom are 6. But one thing to realize is that if you had all of this information over here, you could actually figure out this last piece of information. So you actually only have 5 degrees of freedom. When you have just kind of n data points like this, and you're measuring kind of the observed versus the expected, your degrees of freedom are going to be n minus 1, because you could figure out that nth data point just based on everything else that you have, all of the other information. So our degrees of freedom here are going to be 5. It's n minus 1. So our significance level is 5%, and our degrees of freedom degrees of freedom is also going to be equal to 5. So let's look at our chi-square distribution. We have a degree of freedom of 5. We have a significance level of 5%. We have a significance level of 5%. And so the critical chi-squared value is 11.07. So let's go to this chart. So we have a chi-square distribution with a degree of freedom of 5. So that's this distribution over here in magenta. And we care about a critical value of 11.07. So this is right here. We actually even can't see it on this. So if I were to keep drawing this magenta thing all the way over here, if I were to just keep, if the magenta line just kept, the distribution just kept going over here, you'd have 8. Over here, you'd have 10. Over here, you'd have 12. 11.07 is maybe someplace right over there. So what it's saying is the probability of getting a result at least as extreme as 11.07 is 5%. 5%. Our result, so our critical chi-square value. So we could write even here. Our critical chi-square value, is equal to, we just saw, 11.07. Let me look at the chart again. 11.07 is equal to 11.07. The result we got for our statistic is even less likely than that. It's even less likely than that. The probability is less than our significance level. So then we are going to reject. So the probability of getting that is, let me put it this way, 11.44 is more extreme than our critical chi-square level. So it's very unlikely that this distribution is true. So we will reject. We will reject what he's telling us. We will reject this distribution. It's not a good fit based on this significance level.